Okay, so good to see everybody here today. We're gonna jump back in talking about traveling waves, starting off with some more information on sound and light. I just wanted to briefly mention that I did just post the quiz 3 and the homework 3 scores, as well as the solutions for quiz 3. I'm really impressed. I think people did really well on quiz 3. On average, I think the average score was like in the around 80%. So most people either, I think, got them all or missed the hard one that I do admit it was quite a tricky unit conversion problem. But I recognize that there were a lot of people who struggled with this quiz. And so please feel free to come to office hours and chat with me or shoot me an email. And I'd be happy to help you see where you could improve. And I did decide to give partial credit if you got one of the solution branches, but not the other, for finding the time. So hopefully that helps some people. If you see your score with a like 2.5 or 3.5, that's what happened. Okay. So back to where we were. So we were talking about, just to recap, the speed of sound and how we can find it in different materials. So for gases, we can use thermodynamics and think about how the speed of sound, so sound waves in general, are adiabatic processes and that they don't involve the transfer of heat. So we have this thing we call gamma, which is the constant pressure heat capacity divided by the constant volume heat capacity of the gas. And if you do this out, it ends up being d plus 2 over d, where d is the number of degrees of freedom. So for a monoatomic gas, this would be 3. For a diatomic gas, this would be 5. And for a solid, this would be roughly 6. And so we give some speeds of sound in different materials. You can see that cold air is one of the slower speeds of sound, but it's also one of the more relevant for calculating important sonic quantities. But that instead of using thermodynamics, we can think about the speed of sound in terms of material properties. And in that case, it's very similar to how we had an omega, which is a root k over m. And remember, omega here isn't a speed, it's an angular frequency. But it turns out that the speed of sound in a material, since sound and all traveling waves are the result of lots of oscillators being connected together such that they can pull and tug on each other. So when one starts oscillating, it kind of sends that information on board. So as a result of this connection between oscillators and traveling waves, we get a really similar expression for the speed of sound in materials, where B is the bulk modulus, which in a solid is sometimes called the Young's modulus, which basically just tells you how stiff that material is on a molecular level. So in the same way that K is the stiffness of a spring, so a larger K value, like if you have a K of 1,000 newtons per meter, you're talking about a stiffness of like a car shock absorber. Similarly, this B tells you something about the stiffness of that molecular structure. So you can see for something like diamond that has a very regular crystal, that the bulk modulus is on the order of a few hundred, whereas for something like chalk, rubber, sandstone, you can imagine those materials are very easy to break apart, kind of dusty, that you get a much lower bulk modulus. So it's telling you something about the springiness, basically. And the rho here, this is the mass over volume density. And so that's telling you something about the mass of the material. So if you're trying to remember these formulas, and remember there was another one for the speed of some wave on a string, which was the square root of t over mu. So all of these speed formulas end up being basically the square root of something telling you about the stiffness of the system divided by something telling you about the weight or the inertia of the system. yeah, I really shouldn't say weight, because these are also valid in regions without gravity. So it's really telling you about the inertia, how much something resists motion, which is a property of mass. And then we plugged into the thermodynamic speed of sound equation here to get 343 meters per second, which is a pretty good estimate for the speed of sound at everyday temperatures and humidities on Earth. And so this is the value that you'll want to use in all of your homework problems, unless you're told otherwise, unless it's like sound traveling through the ocean or sound, and they tell you a temperature that's not 293 Kelvin. And importantly, if you do get problems with some temperature in Celsius, you can use this empirical formula to quickly estimate the speed of sound based on that temperature. There are other important factors that affect the speed of sound. So notably, composition comes into play via that gamma factor. And also the mass, the molar mass. And so if there's more humidity in the air, that's one of the main ways that the speed of sound is changed. But temperature is primary. And so that's why we have these sorts of formulas. And it's good practice to use these things, this bottom left formula, because a lot of the time, honestly, when you're professionally trying to solve any sort of, for any sort of quantity, usually there's like someone has done a lot of experiments and they just hand you a formula and maybe it's rather tricky, but you just have to note what the required values are and plug them in to get the thing that you're interested in. And then I think the last thing I said last week was that you can use the speed of sound to measure roughly how far away lightning strikes are occurring. That basically, if you're standing over here and there's some lightning strike over here, that the image of the lightning strike is going to travel to you at the speed of light. So you'll see that bright bolt of lightning, and that will take a super small amount of time. We'll talk about that momentarily, how long that takes. But basically, light travels about 1 million times faster than sound. So it's we can almost neglect the amount of time. So this is sort of almost instantaneous. Whereas the sound, so the thunder, that travels at a much slower speed. So 343 meters per second, just for context, this is around 700-ish miles per hour. So it's fast, much faster than normal human transport goes, although, jet airplanes can travel this fast. But it's not, ridiculous, basically. It's not like the speed of light, which is literally the fastest that anything can travel in the universe. And so the amount of time that it takes to hear the thunder will just be, if we think about the equation V equals D over T, this is going to be D over V. And so I guess I should write this the other way around, because so we measure the time between when we see the image and when we hear the thunder. So we could call that delta T. And then the distance that the lightning is away is just V delta T, where this V is 343 meters per second. So for example, if you saw a lightning strike in the distance and then you count to yourself 1, 2, 3, maybe after 4 seconds you hear the thunder, then you could do 4 times 343, you get roughly, 1,400. And so that's telling you that that lightning strike is about a mile away. A mile is 1,600 meters roughly. And so it's a really convenient way to estimate distance in these situations, but importantly, thunderstorms are very big spatially, so don't use it as a prediction for if the thunderstorm is traveling toward or away from you, because it could just be happenstance that you're hearing lightning strikes on the front of the storm versus the back of the storm, and you think that it's traveling towards you, or you hear them on the back and the front and you think it's traveling away. So it's hard to use this information to estimate direction. Okay, and then some of you may be already on your way to becoming experts on the images in this slide. So these are pictures describing this technology of ultrasound or ultrasonic imaging. And we will see lots of problems with this because the MCAT loves to ask problems about ultrasound. And so I'm going to make sure you see quite a few of them. And it's really a great technology to connect a few different pieces, which is, oftentimes when you are thinking about the principles you learn in a physics class and you go to build something, you're going to use lots of different parts of that physics knowledge. And ultrasonic imaging is a great example of that. So just by thinking about how long it takes, okay, first of all, some background. So the way ultrasonic imaging works is that we use a really high frequency, so a quickly oscillating sound wave, which is imperceptible to human hearing, so above 20 kilohertz. And we use that kind of sound wave because of its material properties in relation to the human body. So these ultrasonic waves have really nice reflection coefficients at the boundaries between different materials. So they allow us to tell where is their tissue of, where is their muscle tissue, where is their bone, where is their fat, and basically paint a picture of the body. And so one of the ways that we do this is by thinking about how long does it take for that reflected bit of ultrasound to come back to our detector, which is just a simple use of this, V velocity is distance over time. And so if we know what the velocity of sound is in a bunch of different materials like the skin and muscle and fat, then we can kind of add these things together and start to paint a picture of what the ultrasonic imaging is trying to show us. And those reflected waves basically occur at the boundaries between materials. And we'll talk a lot more about this as we get into optics. But a good general principle to know, even at this stage in the class, is that whenever you have any kind of wave and it travels from one material to another material, stuff is going to happen, interesting stuff. So some of that wave's energy will be transmitted from the first material to the latter, and some of it will be reflected. And the proportion that's transmitted versus reflected depends on the material properties of those two materials. So basically, how fast is the wave traveling through the materials is the primary important property. And so you may have heard of this in terms of Snell's law if you've taken high school physics, and we'll certainly talk more about that. But it's also true in the context of sound waves as well. And so you can see this is an example ultrasonic image where we get some reflection at this first boundary layer, and we can measure how long that takes to happen to get how far away that is. And we measure some secondary reflection at this boundary layer. And so just from those two pulses, so your transmitter is emitting a bunch of sound waves, and then it hears a pulse, and then a moment later it hears another pulse. Just from that, you can already tell that there's some object, some width, that's a certain depth under the skin and that location. And we'll talk later about Doppler ultrasonic effects, where we can also measure the speeds of things. So if your blood is flowing, you can tell how fast it's flowing using ultrasonic imaging as well by looking at how the frequency changes. So a lot of technology comes together in producing these images. And that's actually something really marvelous in medicine in the last 70 years, is that tons of modern physics techniques have all come together to try to solve this perpetual problem of wanting to see inside a person's body without cutting them open. And so, every branch of physics has had its own solution to this problem. So everything from MRIs, which use magnetic and atomic physics, to PET scans that use antimatter in the body, to all sorts of like gamma ray emission topography, any type of physics you can think of, there's someone using it to take pictures inside a person. So kind of crazy. Okay, so that's on the speed of sound. Now on light speed, which like I mentioned is around 300 million meters per second, so about 1 million times higher than the speed of sound in air. Remember, the speed of sound in air is roughly 343 meters per second. So around a factor of 1,000,000 between these two. We have the speed of light. And I think it's reasonably common knowledge maybe now that the speed of light is the fastest speed in the universe. And so you'll learn a little bit more about this in 3C. But basically, no matter how much energy you have, no matter how big of a rocket, you can never get to that speed of light. So the speed of light is the speed that massless objects will travel at in the universe. So any massless object you have, it just turns out that the particles that light is comprised of, photons, are massless. So they travel at the speed of light. But there are other massless particles in the universe, gluons and other things, and they all travel at the speed of light. So it's just a speed of massless objects. And basically, massive objects can never get to this speed. And the crazy thing about the speed of light is that it doesn't follow normal velocity addition formulas. So for example, if I'm on a train and I throw a baseball and someone's standing on the ground next to us, they would see that baseball traveling at the speed of the train plus however fast I throw it. So you can cause that baseball to look like it's going a different speed based on if you're standing in the train with me or if you're standing on the side of the tracks. You'll see it traveling faster in the latter case. If I shine a beam of light, like if I turn on a flashlight on the same train, and I measure the speed of light, I'll get 3 times 10 to the 8th meters per second. And no matter how fast that train's going, someone sitting on the side of the tracks would also see the light traveling at the same speed. So light's really weird. It doesn't follow the normal rules of relativity, and that's why Einstein developed special relativity. And I just wanted to say, this is really cool. Both of these pictures on the right were actually taken in Irvine. And one of the most accurate measurements of the speed of light was actually made in Irvine by Michelson and Morley, whose names are on streets in the area. So if you're driving down Michelson or Michelson Street, it's named after famous experimental physicists who measured the speed of light. And there's a whole side story there, but we don't have to get into it. And I should lastly mention, this is the speed of light in a vacuum, and that's the thing that's actually a constant of nature and that nothing can exceed. When light travels through a material, we observe it actually going slower, and we'll talk a lot more about that. It's really the whole reason that lenses are able to work is that the light is traveling a little bit slower in the glass of your glasses or in the plastic. And so that effect causes light to bend as it travels between the air and the glasses, for example. But air has a low enough density that the speed of light in air is basically 3 times 10 to the 8th meters per second. So it's pretty, to good approximation, true that we can use the speed for light in air or in space, basically. And sorry, I just keep throwing facts about light out, but sound has a medium that it travels through, which is a gas or a solid, and ocean waves have a medium they travel through, which is the ocean. But light, its medium is the electromagnetic field, which exists everywhere in the universe. And so light can travel through the vacuum of space, and it doesn't need gas particles to be bumping into each other, for example, for it to be able to go from one place to another. So that's why we see the sun, but we don't hear the sun, which is really lucky because the sun would be very loud if we could hear it, which is kind of a weird thought. But anyway, so yeah, light, really beautiful. We'll talk more about it. It's this speed, the fastest speed in the universe, but it's only true in vacuum. Good approximation true in air. And it's actually how we define the meter as well. The meter is defined in relation to the speed of light. There's actually so this is exactly the speed of light in a vacuum, and that's the what gives us the definition of a meter. But you don't need to know that value. You just need to know the 3 × 10⁸ one. Okay, and as you, I'm sure, already know, but it's good to talk about now that we're freshly looking at light and traveling waves. There are lots of different kinds of light that we collectively refer to as electromagnetic radiation. So the word radiation, sometimes people think of as some scary thing. And it's true that these gamma rays and X-rays are the scarier forms of radiation in the sense that they're ionizing radiation, meaning that the waves have enough energy that they can rip the electrons off of your atoms, which really messes with like your DNA and gives you some genetic mutations, for example. So those two are a scary type. And I guess ultraviolet can also, to some extent, mess up biological processes, which is why we get skin cancer from staying out in the sun too long. But for the most part, the word radiation in physics just means some traveling wave, effectively. And oftentimes it's exclusively used for traveling waves of the electromagnetic variety, so light. And I think this plot is really nice because it has a lot of information on it. And so notably, it has the wavelength approximately of each of these types of electromagnetic radiation. So you can see that visible light has a wavelength of around 10⁻⁶ meters. So we often talk about visible light's wavelengths in terms of hundreds of nanometers, which is something that we'll see again and again as we're going through, especially the optics section. And that by the time you're at microwaves to radio waves, the wavelength is at the scale of people. So people are about a scale of 1 meter. So basically, more energetic radio waves are about the scale of a person. So when you're talking on your phone and it's communicating with the cell tower, it does that via radio waves. And those radio waves are similar to the size of your body. With modern 5G, they're a bit smaller, but roughly that scale. And then as we go down to these lower and lower wavelengths, we get higher and higher energy radiation. So an important thing to note in relation to this plot is that for light, if you're thinking about each little chunk of light, each little photon, it will have more energy the smaller the wavelength is. Of course, we can have lots and lots of photons of that type, but it turns out that it is important how much energy each individual photon has, because if each individual photon doesn't have very much energy, no matter how many of them you send at someone, it's not going to do anything. So to a very high level of approximation, you can send a ton of radio waves through a person's body and it won't hurt them at all. In fact, lots of them are traveling through all of our bodies right now due to cell towers and Wi-Fi and all sorts of things. But if you send just a few gamma rays through a person, you can seriously mess them up, especially if they're very high energy gamma rays. So the energy of the individual photons does matter, and that's related to the wavelength of the light inversely. And then also at the top here, this chart tells if that type of radiation penetrates the atmosphere. So the Y means yes and the N means no. And you see that the type of radiation that penetrates the atmosphere is mostly focused around the visible range, which is no coincidence, right? Our eyes evolved to see this type of radiation because it's the type of radiation present on the surface of Earth. Radio waves can also travel through Earth's atmosphere, but we can't see them, and there's no real way that a human could see them, because in order to see a wave, you need some detector that's approximately at the scale of the wavelength. So if you're trying to see a 100-meter long wavelength wave, generally you need something that's on the scale of tens to hundreds of meters. So that's why you'll see these huge telescopes, huge satellite dishes, and that's in order to basically see those sorts of waves. So anyways, I guess before we move on, any questions about electromagnetic radiation? So there's so much you could say about it, but yeah. And nowadays, just as an astrophysicist, I should tell you, we not only do scientists on the ground have ways to detect all of these types of things, of course, but we actually have satellites in every single one of these regions now. For the first time in human history, we can by putting satellites, above Earth's atmosphere, we can see the types of waves that Earth's atmosphere would normally block. So actually, just yesterday, we had a party in the physics department because a new X-ray satellite launched that we're going to use to measure some new properties of dark matter and do our, research. So that's measuring something in this wavelength range that normally the atmosphere blocks. So we put a telescope above the atmosphere, which is very expensive, but occasionally somebody will agree to pay us enough money to do so. So anyways, like I mentioned, light has this fundamental speed, but that's only true in a vacuum. And so when light travels through a material, it slows down. It can't speed up. The speed in a vacuum is as fast as it or anything can possibly travel. So it can only slow down. And we talk about how much it slows down in terms of some number called the index of refraction. So this number n is the index of refraction. And n has to be either 1 for the vacuum or bigger than 1 for a material. And you can see that, so c is a letter that we reserve in physics. Sometimes you'll see it for any velocity, which is really confusing, but generally it's reserved for the speed of light in a vacuum. And so c equals nv, where v is the speed of light in a material. So you can see that the speed of light in a material, it's basically c over n. So the bigger n is, the bigger the index of refraction, the slower light travels in that material. So light travels very slowly in diamond, which is actually, so we talked about how you can tell if a diamond is real by looking at its thermal properties. So it has a very high thermal conductivity. So if you put a hot thing on one side of your diamond and a temperature probe on the other, if that heat travels very quickly, you can say it's probably a diamond. You can also test it by looking at how much light refracts. And we'll see that due to that slower speed of light in a diamond, it causes light to bend rather dramatically, which is actually one of the properties people like about diamonds, because it can allow them to have these very shimmery sorts of, resulting appearances. But anyway, so you can see here that for air, the index of refraction is very, very close to 1, which is why we can just take the speed of light in air to basically be c, that 3 × 10⁸ meters per second. But for other substances, even though they're clear, we do have to be careful. And so starting with things like water, n is large enough that we actually should adjust what speed we're using when we're solving problems. So if you're in your homework and you're having trouble, you've plugged in the speed of light, make sure that you're paying attention if it's something where the light's traveling through a material, because its speed will be different. And I'm not going to get into the details because we really don't have time, but it's good to know roughly why light travels more slowly in materials. So there are a lot of really bad explanations of this. As someone who has been very interested in this and studied it a bit, I'll tell you that if you're trying to explain it simply, the best I can do is that when you're traveling, so light is an electromagnetic wave, which means that it can affect and be affected by electrostatic charges, which we'll learn more about in 3C. And so when light's traveling through a material, there are a bunch of electrons in orbitals. So those electrons are effectively moving, and the light and the moving electrons interfere with one another. And as a result, you get a new wave, which is what we perceive as the light in the material, that travels at a slower speed. So that's kind of the quick explanation. It's a really tricky phenomenon, but as you can see, very important. It's the basis of all optical lenses, so microscopes, telescopes, all those sorts of things. Okay, and The frequency of a wave is fundamental. So the frequency just comes from how fast the source moves. The speed of the wave is dependent on the material. And so as a result, the wavelength will also change. So the wavelength of light in a material will be the original wavelength or the vacuum wavelength over the index of refraction n. So just watch out for that. It'll sometimes be important. Okay, so to try a problem with this, light wave travels from left to right through 3 transparent materials of equal thickness. Rank in order from largest to smallest the indices of refraction in 1 and 2 and 3. Okay, so we just saw that lambda equals lambda in a vacuum over n, where lambda is the wavelength. So that's the idea of measuring the distance between 2 similar points on a periodic function. And so which of these materials has the largest index of refraction? So if that n is bigger in this formula, what happens to lambda? Good, it gets smaller. So which of these has the smallest lambda? This one. So this in 3 is the biggest index of refraction. So light's traveling very slowly through that material. And then next would be N1, and then finally would be N2. So you can see just by looking at the wavelength of light in these materials, not only can we think about how, or I guess it's all related. So by looking at the wavelength, we can think about how fast the wave is traveling. So light's traveling very slowly through material 3, but rather quickly through material 2. Okay. So far we've just been looking at sinusoidal waves in the context of, one big sine or cosine stretching out infinitely in both directions, where the whole function is being shifted as time ticks on, such that we get something that looks like a traveling wave. But in reality, when we make waves, we almost always make them in either circular or spherical patterns. And, this is really a question of the geometry of the system. So if you have something like water, there's a one-dimensional boundary where the wave exists, or sorry, a two-dimensional boundary where the wave exists. So the ocean, you can think of the surface of it, which is flat. So like an XY plane. And as a result of that, when you, let's say, have a little bit of water droplet fall on the surface, like you see in the fountain outside, what happens is every direction looks the same to that disturbance. So it will cause a circular wave to start spreading out from where we dropped that little bit of water. So if you look at either a fountain or when rain starts to fall and it hits the surface of water, you'll get little circular waves traveling outward. But the important thing is that those circular waves still have peaks and troughs. And so if we took a slice of them, they would still look like sinusoidal waves. Okay, so everything we've been learning about sinusoidal waves so far, we can apply even if those waves are circular or spherical, as long as we're just thinking about slices of the wave. But as it spreads out, the energy of the wave will also spread out. And this is why, when you draw these waves, they just look like they're going to endlessly stay the same. But we know in reality that, for example, the people farther away from me right now can't hear me quite as well as the people close. And so as I'm speaking, I'm, creating these wave fronts that are spreading out. And the farther they spread out, so we can think of kind of the area of the boundary, the less energy that wave will have. And so in the case of sound, where the wave is traveling in this full three-dimensional, volume of air, whenever you produce a wave, like me talking right now, those waves will spread out as big spheres, spherically. And so we can think about how they'll lose energy, and it's related to how big that sphere is at a certain radius, we know the area of a sphere is 4 pi r squared. So if I go twice as far away, my wave, since it's had to spread out, it will have decreased in energy by a factor of 4. So twice as far away, the surface of that sphere from the wave is 4 pi r squared. So twice as far away, that area is going to be 4 times bigger. And so we can see this when we write the wave equation for these spherical or circular waves. This A of r is telling you that the amplitude of these waves changes the farther away from the source you get. So for a circular wave, this A of r will be proportional to 1 over r, because the circumference of a circle is 2 pi r. So the circumference is 2 pi r. And so the energy has to spread out over that circumference, bigger and bigger circles as the wave spreads out. And so you'll lose energy that way. Whereas for a spherical wave, like sound waves generally are, our A of r is proportional to 1 over r squared, because the area of a sphere, like I said, is 4 pi r squared. So I forget if there are homework questions that use this idea. I think there's maybe one where we're thinking about how spherical waves, they look almost the same mathematically. They still have this sine function, except instead of x, you can see we use the radius r here. But it's, that's just saying we can take a slice of the wave radially and it'll look the same, except for the fact that the amplitude decreases as we get farther away. And you don't need to know the exact formula for the amplitude, just how it's related to the radius. So for circular waves, it's 1 over r, and for spherical waves, it's 1 over r squared. And then like the image shows here, as we get, when we're close to the source, those circles look like circles, but as we get farther away, we can see that those wave fronts get to be more and more parallel to each other. And so that's where the idea of, standard traveling sinusoidal waves comes from. Almost all sources of waves will create either circles or spheres. But once we're far away from the source, it'll look like those waves were just nicely, with parallel wavefronts. Okay, so I know this is tricky stuff. Are there any questions about these circular or spherical waves? Either why they're natural, why they become like standard straight line waves as they get farther from the source, or what these relations are describing? Yes. Very good question. So no, so you can see that here, but this is really important, so I'm glad you asked. You can see that we assume that the wavelength stays the same for spherical and circular waves in these contexts. Water is really weird. So water, like ocean waves, are a good thing to think about in your head because we've seen them so many times, most of us. They're really familiar. But water just behaves very strangely in the sense that for water, waves with different frequencies travel at different speeds, which is not true for our light and sound waves to good approximation. And so in water, it looks like the wavelength is changing oftentimes, but that's just because different types of waves will travel at different speeds. So it'll kind of spread things out or cause the shape to change. So you might be asking this question from that context. If so, water's weird. As we've seen, I think that's the only thing that connects all the topics in this course from fluids to thermo to waves, is that water's pretty weird. But yeah, the wavelength we can take to be the same no matter where we are in relation to the source. Okay. And so then they throw this into the same section, section 16.5. So I just wanted to make a note of that. If you're looking for where in the book they talk about phase difference, it's in section 16.5. I don't know why they put it there. It's not really a principle of spherical or circular waves, but here we are. So we talked about phase already, which is how in an oscillator, instead of being a pure cosine function, maybe we start the oscillation by flicking it and pulling it back, in which case that oscillation would be some shifted sinusoid, and we say the amount that it's shifted angularly, we call that the phase. But we also use phase in physics in the context of a phase difference, which is basically if you have two waves that are identical in wavelength, the phase difference is how far apart are similar points. So for example, how far apart are, well, here they're using it not in the context of similar points, but just for points x1 and x2. But we'll talk in more detail about the importance of, for example, if we have a wave like this and a wave like this, we'll often try to find the phase difference this delta phi. So we'll often find the phase difference between similar points on two separate waves. But like the book's example here, we can also talk about phase difference in the context of two different points on the same wave. And basically, the phase difference is just if you think of each point in terms of an angle, so in terms of what the argument is that we feed into the trig function, then we can subtract those angular positions, and that angular difference is the phase difference. So anytime you hear phase, you should be thinking this is going to be something in radians, basically. And so you can see what they're doing in this picture is we have this point x1, and we know that the our wave equation, d of x comma t, is going to be something like a times sine of kx minus omega t plus phi naught. And so this whole thing is the phase at point, x comma t. So that's what they're calculating here is phi 1. And then they're doing the same thing at a different point in space, x2, but at the same time. So they call this phi 2. And then the difference between those points, phi 2 minus phi 1, is what they call delta phi, which is the phase difference. And instead of going through this whole process, you can see that the omega t and the phi naught are going to cancel. So we have this easier formula here for you to find the phase difference between 2 points. So if we know that one point is located at 2 centimeters and another point's located at 4 centimeters, then we can just find that delta x, so 4 minus 2, which would be 2 centimeters, divide it by the wavelength, which is a way to convert between length and angle, basically. And so maybe the wavelength is 1 centimeter, so we would get 2 there, and then multiply it by 2 pi. So delta x over lambda, that's the fraction of the wave, and multiplying by 2 pi turns that into a value in radians. And putting it all together, we get a phase difference, delta phi, which, like I said, just tells you the angular separation between 2 points, and it's often used to talk about the angular separation between the same point on 2 separate waves. So when we get to the next chapter, chapter 17, which is on interference, this will be a really important idea. So that's why, even though it's in a weird place in the book and the presentation's a little strange, I think it's good to see it now so that it feels more familiar later. Because basically these phase differences will tell us how 2 waves combine, which is what we call interference. Okay. So then moving on to section 16.6, I guess before we do that, it's about halfway. So we'll take a 5-minute break and then we'll dive back into the physics. And I don't know, maybe if there are questions about the phase difference, feel free to come up and ask or hold up your hand, whatever's easier. Yeah, I can I can leave this one up if people are wanting to see it. Okay, so we should probably try to get back into the slides now, but hopefully, halfway break continues to be helpful. I know it is for me. Were there any questions about the phase difference slide now that we've had a bit to process it and chat and everything? Okay, so power intensity in decibels. So we've talked a lot so far about the frequency of waves, the wavelength, the wave number, angular frequency, all these different properties telling us how much and quickly they're oscillating. But it's also important to talk about the amplitude. So we've mentioned it briefly. We talked about how for a circular or spherical wave, it'll die off as we get farther from the source because that energy has to spread out. But there are some important tools that we can apply to quantify how much energy some wave has. And so if you don't take anything else away from this section, I just want to teach you how to buy a light bulb, because it's very confusing and connects quite well to what we're doing right now. So when we talk about power, the power that something emits, some source of a wave emits, is telling you the total amount of energy per time coming from the source. Okay, so for a light bulb, we can imagine that there's some amount of energy leaving that light bulb, and that because the light bulb continues to be on, that there's some amount of energy being emitted in each chunk of time. And if we quantify the energy in terms of joules and the time in terms of seconds, then that composite unit is known as a watt, which is the SI unit of power. And so a watt tells you, roughly that something is emitting 1 joule per second. But for the context of a light bulb, we have to be careful, because light bulbs, depending on how they're made, not all of their energy will be in the visible spectrum. Okay, so remember we saw these radiative emission curves before that have a frequency versus intensity. And they looked, something like this. And so these curves, which are known as the black body curve, depending on the temperature of the object, maybe this region would be in the visible range, but a significant fraction of the energy emitted by something that's radiating like a black body is not visible to humans. And so the wattage number of a light bulb is telling you the total amount of energy per second that is being emitted in every frequency. So it's adding all that energy together. And the reason you care about that as someone buying a light bulb is because that's how much electricity that it will consume, right? Whatever it's emitting via radiation, that's what it has to consume from the plug that it's, plugged into. And so that'll determine your electricity bill. But we also care about how bright the light bulb is. And when we only had one type of light bulb, so back in the olden days, the only type of light bulb was the incandescent bulb, which basically works by heating up a very thin wire, very, very hot, which causes it to emit like a black body and create this curve we see here, where most of the energy isn't visible. And in fact, even for a very hot tungsten filament in the last batch of incandescent bulbs that were produced before they were discontinued, it only got to a temperature of a few thousand Kelvin. So most of the energy at that point was still in the infrared. So incandescent light bulbs primarily emit heat, basically, not light. So back in the day when that was the only kind of light bulb, we could use the wattage to tell us about the brightness. People would have just seen what a 60-watt light bulb looked like. They would have seen what a 40-watt light bulb looked like. And since there was only one type of light bulb, they could just say, that wattage is proportional to the amount of light. And so they would say, well, this is as bright as a 60-watt light bulb. But nowadays we have lots of types of light bulbs. And actually most people don't use incandescent bulbs because they emit so much of their energy in the infrared. Most people prefer LEDs, which work by entirely different physics. So instead of creating a curve like this, LEDs create a curve like this, where almost all of the light is in the visible range. And the way they work is quite complicated beyond the scope of this class, but I encourage you to look it up if you're interested, or to ask me. And so you can see that they consume significantly less energy, about a sixth as much. But that they, the 60-watt incandescent bulb is producing about the same amount of visible light as the 10-watt LED bulb. And so we develop a new unit known as the lumen, which is talking about the intensity of visible light. So lumens are effectively a scaled up way of talking about how much power is being emitted in every direction by a light source in the visible range only. So they tell you more directly how bright a light is. So a 60-watt bulb, which is kind of like a normal brightish light bulb, emits around 700 lumen of light. And that's the total amount of energy in all directions per second in the visible range. You'll also see light bulbs listed in terms of candela or candles. And that's similar to lumens. It's just talking about visible light, but it also is thinking about the angle that it's emitted in. So candela is more important in flashlights where you're trying to make a beam of light. So by having a more candle worth of flashlight, you have a more beamed source of visible radiation. So anyways, those are the things that go into the brightness of a light bulb. You'll also see light bulbs sold where they'll say some number of kelvins on the side, and you'll have to pause and be like, what the heck, is that real? So for an incandescent bulb, that is actually representing a temperature. Incandescent bulbs, the filament gets very, very hot, thousands of Kelvin. And remember that the higher the temperature, the bluer the light. And so effectively, when you see kelvins listed, like maybe you see 5,000 Kelvin listed on a light bulb package, that's telling you something about the color of the light. So a 5,000 Kelvin light will be more of a crisp white color, whereas something like a 3,000 Kelvin light will be more of a red, like people think of them as more like a natural light color. And so effectively, when you're buying a light bulb, you want to keep these three things in mind, right? How much energy does it actually consume, which is the wattage, and that also happens to be the amount of energy that it outputs in all frequencies. How much energy does it output in the visible frequency, which is the lumens, and then what color is the light, which is represented by a temperature in Kelvin that the black body curve would be centered on. And so there are a lot of people who do construction that don't really know where these things come from and just know what the numbers look like. But hopefully, by being in this class, you can actually understand a bit more about where these numbers are coming from. Okay, so we can take the power that a light emits, or that a source of sound emits, any source of waves, really, and divide it by an area to get the intensity. And so this intensity, sometimes it's also called a flux, which is a word you'll see many times in your future if you're taking 3C, next quarter or something. And so the intensity tells you sort of the concentration of energy, right? Because if we have a light that's emitting this power, some number of joules per second, depending on how that light is concentrated, maybe we put a mirror behind it and concentrate it all into one direction, we know that that's going to look brighter than if we just let it, radiate in every which way. And so by dividing the power by the area that light's passing through, we can think about effectively the, observed brightness in that lit up region. Or for sound, we can talk about how loud something is in the region where that sound is present. And again, by thinking about this, if we have something like a light or a source of sound, like a speaker or a person, the power that's being emitted is just going to be some constant, generally. But the intensity is the power over the area. And if we're talking about a light bulb or a person speaking, in those situations, we're producing spherical waves. So that area will be something like 4 pi r squared. The waves are spreading out over the surface of a sphere, and those spheres are getting bigger and bigger as they travel farther away from the source. And so we can see that the intensity is proportional to 1 over r squared. So if we get twice as far away, the intensity, so the brightness of a light bulb or the loudness of a sound, is going to be 1/4 as big. If we get 3 times as far away, it'll be 1/9 as big. And so this is called an inverse square law. And this is true for anything that's spreading out evenly in all directions. So when you learn about electric fields in 3C, you'll learn about Coulomb's law, which also has a 1 over r squared in it, and that's because the electric field spreads out evenly in all directions. When you learn about Newton's gravitational law, the gmm over r squared, that also has an r squared in it. So you'll see tons of r squareds in physics. Every time you see one, for the most part, it'll be communicating to you that some energy is spreading out evenly in all directions in 3 dimensions, therefore spreading out on the surfaces of bigger and bigger spheres, such that we get this 1 over r squared showing up. So you'll see this all over the place in 3b and in 3c. And it's really important in health and safety applications. So when we're talking about sound, we'll see this in a minute with decibels, but there are dangerous levels of sound. And one of the best things you can do is in these situations is get farther away. So if you get twice as far away, the intensity of sound drops off by, a factor of 4. And this is also true with radiation. So when you are learning about radiation safety, so I helped develop a radiation safety course myself, actually. One of the principles of radiation safety is to be as far away from whatever is radioactive as possible. Because just by being far away from it, you're dramatically decreasing the flux, the intensity that your body experiences. And so, one of the main things that you want to do when you're designing systems that involve radioactive components is make the radioactive stuff sort of sealed away far away from people. Okay, so we have a practice problem. I know I've just been blabbering on for a while, so it's good to have one of these. So a typical red laser pointer emits 1 milliwatt of light power into a 1 millimeter diameter laser beam. What is the intensity of the laser beam? Okay, so a pretty straightforward practice problem, hopefully. We have that intensity is power over area. And a laser is an example of a situation where we don't follow that inverse square law. Because if you've ever seen a laser beam, it doesn't spread out very much. It just stays very concentrated. And that's due to the way that that light is produced in a very special chamber that gets all of the light rays basically synchronized and emitted in such a way that they're all sort of stay and stuck together. But anyways, so for a laser, we just have, to a very high degree of approximation, a non-spreading area that all of that energy is being focused onto. And we can just divide. So we have 1 milliwatt of power, and a 1 millimeter diameter means that we have pi times 0.5 times 10 to the minus 3 meters squared here. And so to get the intensity, we just have to plug into a calculator. And when I do this, I get 1,300 watts per square meter. And so, the takeaway from this is that with a laser, because you're keeping all of that power in such a small area, you end up with a crazy high intensity, right? When we were talking about light bulbs, so this is a 1 milliwatt laser. A minute ago, we were looking at, 10 watt LED light bulbs, for example. But that 10 watt light bulb, even if you're really close to it, you'll struggle to have the intensity that we just saw with that laser, right? Because that light bulb has a spatial size and it's also emitting in all directions. So that energy is spreading out. Whereas for the laser, it's very focused. And in fact, if we shine this laser through a lens, we can make it such that it's focused even on a smaller area. And by doing that, we can have these laser surgery tools that can, burn flesh or vaporize the lens of your eye so that you can have your vision adjusted, or cauterize some blood vessel. So very useful tools because we can concentrate this energy in such a small area that we don't damage the surrounding tissue, or that we can do very precise excisions of material, like in the case of LASIK eye surgery. Okay, and so I guess there's a slide about the inverse square law, so maybe I got a bit ahead of myself. But you can see the sun is a great example of this, where the intensity of solar radiation on Earth is basically due to the fact that we have the sun out here, and then we have the Earth at some radius. And at that point, the sun's light has spread on a sphere in every direction. And so the intensity of sunlight that we see on Earth is the power of the sun, which in astronomy we call the luminosity. Luminosity, if you hear that word, it's just the same thing as power, divided by 4 pi, where the r here is the radius of Earth's orbit. We have to square that. And so I think there's a homework question about this. But this intensity that you get is a really important value for solar panels, because it tells you with maximum efficiency what is the most energy you can get from a square meter of solar panel, right? The intensity is a watt per square meter. So if you're trying to build a solar farm, or if you're trying to just put solar panels on your roof, this is the maximum number, or whatever the luminosity of the sun over 4 pi r squared is. And then in reality, if it's at some angle, you're gonna have a cosine in there, which is gonna make it such that there's less intensity on the panel. Or if there are clouds in the way, there'll be less intensity. And then you also have to think about the efficiency of that conversion from solar energy to electrical energy, which is gonna be at best maybe 30%. So as a result, this is really just a sort of upper cap on the intensity that you see there. Okay, so then lastly in this section, we should talk about decibels, which, yes, there was originally a unit called a bell, and a decibel is 1/10 of a bell. That's the root, or the metric prefix deci. But we don't use bells anymore because they were designed for telegraph lines by the Bell Company, named after Alexander Graham Bell, the inventor of the telephone. But we still use decibels because they're a very convenient unit for talking about the apparent power of sound. So for a decibel, what we're doing is first we have to think about the intensity. So this is a power over an area. And then we're dividing that intensity by some reference value, which we can see here is 1 times 10 to the minus 12 watts per square meter. And the reason we use this reference value is because that's approximately the lowest amplitude of sound that a person can hear. And so by dividing our measured sound intensity by this reference value, we have a sense of how many times more than the minimum value is the sound wave that we're interested in. Then we take the log base 10 of this value. So what that's going to do is it's going to compress this ratio. So remember, the thing you get from taking a logarithm is going to, for large values of that ratio I over I naught, the thing we get from the logarithm will be smaller than the ratio. So if I over I naught is, there we go. So if I over I naught is 10, then if we take the log base 10 of 10, we get 1. And then we multiply the log that we take by 10 decibels. And so for the fraction I over I naught of 10, we get 10 decibels of sound as an example calculation. But what I want you to see is, look what happens when we have, let's say I over I naught is 100. So 10 times more energy. When we take the logarithm base 10 of 100, we just get 2. And so this case, we would only have a decibel reading of 20. So you can see when we increase the intensity by a factor of 10, the sound only, the decibel reading only doubles. And so this causes decibels to have a bunch of weird properties. So one of the trickiest types of questions that is something that apparently is on the MCAT, surprisingly to me, is if you have multiple speakers that all have the same intensity, and you take one away, how does the decibel reading change? And it turns out this is a tricky question because it's not just changing by a factor of however many speakers you've reduced things by because of this logarithm of the intensity. So we'll give you some practice with those sorts of problems, but it's not a trivial thing to do. And so you might say, okay, Cannon, this looks really complicated. Why can't we just say a decibel is I over I naught? Wouldn't that be way nicer to just say how many times more than the minimum intensity of hearing? That's our decibel reading. The reason we don't do this is because human ears are actually logarithmically sensitive. And in fact, most sensors have logarithmic gain, meaning that they experience waves that are, for example, 10 times stronger. They experience that as maybe a factor of 2 or a few times more intense. So this is true for our eyes experiencing light. This is true for our ears experiencing sound. And it's true for a lot of mechanical things that we build as well. So a lot of sensors also exhibit this property. So if I play 2 sounds for you and I ask you how many times louder does this sound than that, the answer that you give will be the result of a logarithm of the intensity, roughly speaking. And so that's why we bother to use these types of things. It also allows us to compress this wide range of intensities down to a smaller scale. And so that's what we see here on the right. This is an example scale with a bunch of different decibel values for different sounds. And you can see that we can express everything from the weakest possible sound all the way to the strongest possible survivable sound or painful sound, just between roughly 0 and a little over 100. So the decibel scale is convenient for 2 reasons. One is that it allows us to have a number between 0 and 150 to talk about any intensity. And the other reason is that the human ear is roughly a logarithmic sensor as well. So it's not even a bad way to communicate because of that analogy between the formula for decibels and the way the ear works. And so you can see in this classroom, we're maybe in the 50 to 60 decibel range, depending how far away you are from me, as I'm speaking here. And what I want to draw your attention to, and why I put this formula on the left here, so if you're interested in medicine, there are a lot of painful conditions that result from intense sound exposure. So many of you have probably experienced sound at the 110 to 120 level, but remember that this is a logarithmic scale. So as we go up a little bit in decibel reading, we're talking about a dramatic increase in power. And even though we experience in our brain sound in terms of a log scale, our eardrum doesn't care about any of that. And if it has too many newtons of force applied to it, it'll rupture. Or before that happens, it'll experience significant stress and damage. And so that's why we talk about these allowable exposure times for different intensities of sound. And by the time you get to like 130 decibels, the allowable exposure range is, on the order of minutes. So you should not be listening to these super, super loud sounds for very long. You can look at the maximum decibel output range of any headphones or earbuds you might have, and it'll generally be pretty high, maybe at the 100 to 110 level, and you'll experience that as really loud. Most people can't handle that for prolonged periods unless they already have some hearing damage set in. But like I said, this logarithmic scale means that even slightly higher decibel values are significantly more power, meaning that it's significantly more damaging. So it can sometimes be tricky. And as future doctors or whatever, it's your job to be aware of this, that even slight changes in decibel value correspond to a significant increase of risk and increase of likelihood of damage. And so while we're here, if you're working on the sound project or the hearing project, you may have already encountered this, that there are actually devices designed to make really loud sounds to cause like protests to be disrupted or to people to move. And so these devices not only do they emit incredibly loud sound, but they also have a structure that beams it. So very similar to a laser, you can cause sound to be beamed in a very narrow region, which increases that intensity in that region, and means that over a longer distance, these sounds can be projected and used to cause pain or even permanent hearing damage to people. And so if you encounter one of these systems, what should you do? Well, because of that beaming effect, they can work over long ranges, but they also don't work over a very wide of a range. So you should try to move sideways, basically. And these sorts of systems work at very high frequency, which, as we'll see later, means that they don't disperse as well. So if you get behind a solid object like a building, you'll be much more protected than in an open area. The sound wave can't spread out very easily. So anyways, just an aside. So let's work on this problem. So a blender making a smoothie produces a sound intensity level of 83 decibels. What is the intensity of the sound, and what will the sound intensity level be if a second blender is turned on? Okay, so to find the intensity of the sound, we have to, our beta is 83 decibels, and we'll need to always have this value of I naught ready to go. So it's 10 to the minus 12 watts per square meter. And so that decibel formula was just 10 dB times log base 10 of I over I naught. So let's call this side X for now, just to make our lives a little easier. So we can solve this for I, and we'll have X over 10 equals log base 10 of I over I naught. And then we have to exponentiate both sides to base 10. So we'll get 10 to the X over 10 equals, and the 10 to the log base 10 will cancel, I over I naught. And so finally, and this is a very important relation, but it won't. So on your formula sheet, I'll give you this one, but you'll likely have to get this result we're getting right now by yourself, 10 to the X over 10. This is very important. And so we can calculate the intensity using this by just taking that I naught, 10 to the minus 12, times 10, and then X is our 83 decibels, so over 10 is 8.3. And when I do this, I get 2 times 10 to the minus 4 watts per square meter. So much, much smaller than that laser pointer. But as we can see, an 83 decibel sound is pretty loud. It's like, vacuuming your house, that loud vacuum noise intensity. And so even a pretty small intensity of sound, our ears are reasonably sensitive. So we interpret that as being pretty loud. And so now we can ask ourselves, what would happen if we had a second blender involved? And so the important thing to remember is that if we have a second blender, so our intensity with 2 blenders is going to be twice the intensity that we just found. And so this is going to be 4 times 10 to the minus 4 watts per square meter. And then we can plug this back into our original formula. And so we get our X in decibels that we're interested in is 10 decibels times log base 10 of this new intensity, the intensity with 2 blenders, over that same I naught. And you can see what's going to happen is we're going to increase that original value by log base 10 of 2. And so times 83 decibels. So this is the important idea that I said you may actually encounter even on the MCAT, is that if we double the intensity of the sound, we only increase the decibel rating by log base 10 of 2. And so when we do this, you'll find that it only changes from 83 to 86 decibels. So a very small change in our decibel rating, but you probably, if you've experienced this, probably would agree that this makes sense. So if you have one vacuum cleaner and you're vacuuming your house, and you turn on another one, it's going to get a little bit louder, but not that much louder, because the vacuum is already pretty loud, and your ear doesn't experience this second vacuum in addition as being, extremely significant in terms of the perceived intensity. So are there any questions about this problem? I think this is the last one for today. Okay, so I'll have office hours today like usual, so feel free to either follow me or head there. And otherwise, I'll see you tomorrow.